The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney. Welcome back to the New Quantum Era. Today, it's an interview with Dana Anderson. He has a really interesting perspective. This is going to be on the subsegment of the overall quantum ecosystem devoted to sensing technologies. And I think there's just a lot of room for optimism that this segment of the ecosystem has got, I think, some wild new possibilities.
Yeah, Kevin, absolutely. I mean, I've been looking forward to this conversation because Dr. Anderson's been involved in cold and ultra cold atom systems from their inception in his work at GILA in Colorado, where the first sort of scientific breakthroughs happened for cooling atoms down using lasers, and then developing the applications for that type of device. It's really interesting. And neutral atoms have become a very hot topic in quantum computing over the last year or two. Cold Quanta, which is the name of the company that Dr. Anderson founded, has been joined by QEra and by Pascal as having neutral atom-based devices. And there's more companies that are developing them as well. So it'll be a really interesting opportunity to learn more about the science and the technology underlying that modality.
Good stuff. Let's dive in. Hello, welcome back. And today we have the privilege of an interview together with Dr. Dana Anderson, who is co-founder and CISO of Infleqtion, formerly known as Cold Quanta. He currently serves as this chief strategy officer and is also fellow at GILA, affiliated with NIST, and a professor in the Department of Physics and Electrical and Computer Engineering at the University of Colorado. And since 1993, Dana has been extensively involved in guiding and manipulating the field of cold and ultra cold atoms. Welcome, Dana.
Thank you, Kevin.
Yeah, thank you very much, Dana. We're really happy to have you on. I think we've been really interested in the rise of neutral atom platforms as a new modality of qubits. They seemingly sort of came out of nowhere, even though Cold Quanta was founded way back in 2015. And you've been involved in the development of the science and the technology right from the beginning. Can you sort of tell us how you sort of found yourself in that realm of physics itself, and how your path to quantum information science generally?
Absolutely. Well, I was trained in quantum optics specifically, which is about lasers and optical information processing in the quantum domain many years ago. And I'm an applied physicist. I'd like to do useful things. So as a professor of the University of Colorado in the GILA Institute, my colleagues were focused on atomic physics, and in fact won a Nobel Prize for what's called the Bose-Einstein condensate demonstration, which at the time was acknowledged as the atom analog of the laser. And being an applied physicist, it was very clear to me that this stuff was going to be useful. We wanted to get it out into the world. And so we got a fair amount of funding from DARPA and from various other DoD and NS agencies and NSF to develop the technology, and we wanted to get it out to the world. And that's what gave rise to the founding of then Cold Quanta, which was actually in 2007.
Oh, sorry.
So
Even earlier.
Working there with my colleagues, Eric and Carl, one couldn't help but sort of be pulled into using neutral atoms on the one hand with quantum technology, which was what I was trained in.
Excellent. That's really excellent. And so a Bose-Einstein condensate, that's a form of matter that occurs at these very, very low temperatures. Can you explain, first of all, how lasers make atoms cold? And secondly, what happens at that, what are the properties of that form of matter?
Yeah, very quickly, lasers make things cold in the following way. You know, possibly, that atoms like to absorb a very specific color of light. And so, roughly speaking, you can think of it this way. Temperature is motion, vibration, and so on. And if you shine lasers such that the atom absorbs it, they pick up the recoil of the photons and they slow down, just like throwing maybe ping pong balls at cars. Ping pong balls don't weigh a lot, but if you throw enough and fast enough, you can slow down a car. And so the laser beams shine from all directions can actually essentially stop atoms. Once you stop them, that means they're cold. Once they're cold and close enough together, they form all together a single quantum state. All the atoms become as one, almost as one, but one quantum state. So there's a whole new world at those low temperatures. And the beauty is only the lasers are used to cool the atoms, and only the atoms are cold. So everything else can be at room temperature, while the atoms are in a quantum state. And that's why, as we discuss probably a little later today, um, this technology is so useful for so many technologies, not just the quantum computer, but everything from clocks to quantum networks to navigation systems.
I was going to say, I mean, the involvement of Gila immediately brings to mind, the atomic clock work and other work that's happened in that institute and out of NIST and University of Colorado Boulder. Do you think that what we learned building those atomic clocks, building those other quantum devices, has sort of accelerated the development and the maturation of the technologies behind the neutral atom arrays?
Oh, absolutely. You have to appreciate that the clock in the Gila building is 1,000,000 times more precise than the world timekeeper, the one that keeps US time and everywhere else. And so that factor of 1,000,000 can be, utilized in other technologies. Everything that Infleqtion does involves lasers and atoms, shooting laser beams at atoms to make them behave in useful ways. Clocks on the one hand, quantum computing on another.
That's excellent.
So fascinating. And so much of our audience, I think, is already familiar with many of the other publicized architectures in quantum computing. I mean, transmons and superconductor architectures and so forth. How do we describe at a high level to our audience the, I don't know, advantages and disadvantages and contrasts between the two separate architectures?
Very quickly, of course, you're speaking to an advocate of one modality, and each of us likes our favorite. Okay, so
it's a fun debate. Yeah, there's
filter this.
Yes.
But the advertisement for cold atoms, what we like to convey is that first, there's no fab. Every atom is a qubit, and every atom is just like every other atom, and they're as perfect as can be to begin with. A. B. They are neutral, and we can use laser beams to trap and hold atoms and address them. Everything is done with lasers, and we can have a whole lot of atoms, say 10,000 made of a square of 100 by 100 is not much larger than the diameter of your hair. The truth in lending disclosure is you have to get very good control over these atoms, beautiful, just exquisite control. But there are many other aspects of neutral atoms that make them very attractive for us. And then finally, if you turn the chapter, we haven't finished reading why we like neutral atoms for computing, but turn the pages. We today have ultra cold atom systems operating on the International Space Station. That's how practical the technology is. It's hard to imagine the cryostat, the liquid helium, the big the big chandelier being launched on a rocket. So on the one hand are the arguments that are very fundamental and core and that we'll fight over. Nobody argues about getting cold atoms in space, and therefore we can operate at the edge and tie together compute with sensors and so on, or deploy them in data centers, helicopters, any application arena you like. It's reasonable to talk about putting cold atoms there, quite apart from the discussion about computation.
Yes. So interesting. Quantum edge computing. That's a cool idea.
You've talked about sort of and you've done quite a bit of even recent work, the robustness of that lattice, the atoms held in that lattice is, I think you said something like thousands of G compared to gravitational force is what holds that atom in that optical lattice. Is that right?
Yeah, we slow them down. The force of those ping pong balls against the car, or of the light against the atoms, that's 1,000 Gs. In the lattice, you can tune it anywhere from tens to hundreds of Gs, where G is the force due to gravity. What that means is that if you want to think about putting this technology on a vehicle, an autonomous car, a UAV, that the nasty environment, the vibrations and so on, can be addressed because we're holding on the atoms so tightly. And you think of lasers and atoms as being kind of ethereal, but think of them as bricks and mortar. They're just held there like against all things in harsh environments very protectively. So that's why we do that.
That's really interesting. I love the broad applicability of the technology, because if you think about the earliest days of the electronics industry before it became the information technology industry, right? The focus wasn't necessarily on universal computing. It was on these purpose-built devices like guidance computers and other, single application electronic devices. And we learned so much about fabrication and engineering and all the rest, maintaining reliability in a difficult environment, and all of that fed into the birth of IT itself, the microprocessor and universal computing at scale.
That's good, Sebastian. I mean, you're right, because it's control systems for very rigorous environments, right? Yeah, it was the early dawn of the transistor, right?
Indeed, by the way, and roughly speaking, the way to think about everything that Infleqtion does can boil down to atomtronics, where atomtronics, in fact, has perfect parallels to electronics with an additional richness that the atoms provide because they have internal states. But otherwise, in terms of currents and voltages and waves, it's all the same. But instead of wires, you have light beams to guide the atoms and to control the atoms and so on. So atomtronics is how the company refers to its platform as a whole. And that's the way you can think, we hope, of the evolution, in the same way that happened to electronics, in the late 40s on up to today.
Right. That's really interesting. And so do you think you've sort of shrunk a lot of the components on the atom side of things. Lasers are sort of still like the optical table and optical devices are still fairly bulky. Do you think that there'll be a similar sort of curve, like a progression curve, where the components on the optical side are going to continue to shrink?
Yeah, the existence proof. So first of all, you have it exactly right. If we were on video, your audience would see a little package like this that shows how small the technology is for holding the atoms.
That's about smartphone size.
Yes,
Wow,
exactly
yeah.
right. Very good. So you are right. The challenge is in the lasers, and the existence proof is telecom, where JDS Uniphase, other companies well before them, but JDS Uniphase may be the best known, became powerful by strongly advancing the integration of the photonic technology needed to drive optical telecom. The same thing has to happen here, and very much Infleqtion leads on that forefront, And you'll see us push more and more on what we refer to as quantum photonics, meaning specifically photonics designed to enable the quantum systems based on atoms.
Interesting. And last thing on the sensing side of things, because I thought this is really fascinating too. You're using machine learning to train an interferometer, right? So you've got atoms in an optical lattice. No, sorry. You tell it because I forget what the terminology was.
Well, actually, you said it beautifully. You put atoms in an optical lattice. What is that? An optical lattice is formed when you take two laser beams, for example, going in opposite directions. They create a perfect periodicity of light and dark regions. The atoms like to be in the bright regions. Then you can take altogether 3 pairs of those and make a sugar cube of atoms, for example. And it's absolutely gorgeous, absolutely beautiful application of artificial intelligence techniques and machine learning. And you are right to say we learned how to shake that lattice, that sugar cube, to make an interferometer, to make an inertial sensor, to make a guidance system. Or you can also use machine learning, not specifically to make an interferometer, which is the way we experts think about it, but instead make a very good inertial guidance system. So, the combination of machine learning, sensing, the neutral atoms, and the lasers is really an incredible marriage, which has a lot of headroom and a lot of greenfield for advancing not just the technology for inertial sensing, which is my bread and butter, but many other applications addressing problems like climate change, which is one of the things we are focused on, medical applications, and so on. So we see this as a tremendous forefront for the company.
I was going to say the first thing I thought of, other than just the wow factor to begin with, about that machine learning trained model was I wonder if that's going to give you an advantage over qubit control, right? If you add the state of the atoms into the machine learning training loop, then potentially things like error mitigation or control in general, error correction and fault tolerance are something that you can actually train machine learning models to help improve on the array.
That's an excellent point. I'm going to make a slight distinction. The moment you say qubits, it's almost always used to refer to quantum computing, compute-like, whereas the atoms can do all kinds of things. And then you have it also absolutely right. Actually, machine learning techniques for getting qubits to behave is already used widely.
Oh, we've heard that theme across the podcast. It really is. Yeah, you're right.
It's what's under the hood. Everybody, whether it's superconducting or quantum dots or what have you, tries to get their system to behave better with machine learning. It has a very directed purpose. The machine learning that we do in the sensing and the signal processing, we call it, often is a very high level. I want a good accelerometer, a good RF receiver, and it can tune, to signals of interest. That's, so it's sort of the outward application that the machine learning is used rather than inward of getting the system to behave itself like you wanted it to. But very good points and absolutely on spot.
And so when we are talking about quantum computing, what do you add to, like, from Albert to Hilbert? What's the added components that turn it into a computing platform? And I should say, Albert is the Bose-Einstein condensate device, and Hilbert is your computing device, right?
Albert, we refer to the in several different ways. And by the way, now it has a new name, Oracle with a Q.
That's required by law.
We're trying to bring down Scrabble.
I'm worried that we're going to run out on a global scale of Qs. It's not an exhaustible.
So They are two complementary platforms. You should think of Albert/Oracle not as a BEC machine, but an atomtronics platform where you can develop, think of it as the FPGA, field of programmable board from Xilinx, right? That you get and you want to prototype, does certain things, you want to prototype your application. That's the way to think of Oracle. It gives you the opportunity to simulate and solve sensing problems and signal processing. It's basically analog system, and it has many, many atoms, tens of thousands is a typical number. The Hilbert, our quantum computer, by contrast, has a very specific number. Each atom is very precisely addressed and controlled as an individual qubit. So they operate in completely complementary spaces. In the old days, there used to be something called analog computing, um, for example, but this is Albert Oracle is much more general and makes the development of sensors and signal processing accessible, just like when IBM put their computer on the cloud. Albert/Oracle makes quantum sensing and signal processing accessible to the broader public.
So for the purposes of prototyping applications, is that right? So you're using the ensemble in the Bose-Einstein condensate as a proxy for a single or for a smaller group of atoms, or
Well, typically in sensing applications, the more atoms, the better, first. So, and second, uh, just in a very different way, the atoms can still be entangled. But you're right, it's ensembles rather than individuals, which have advantages in the context of what it's meant for, sensing and signal processing, whereas the quantum computer is meant to be a very precise system that can solve any problem as per general purpose quantum computing. Albert Oracle is meant to be targeted purpose sensing and signal processing.
So, do we interpret it correctly that many of the applications from your venture do they focus more powerfully on sensing, or do you feel like you're trying to I don't know, greet both markets with equal emphasis?
Very good. So here is Dana's view, which is not very distant from the Infleqtion view. Is think of the internet world. Starting with the Internet of Things, you have a sensor. Right behind the sensor, you always do signal processing. Then you send it up to the big boys, the processors. Um, so we can start at the edge with the sensor. And it's especially important in quantum to let the signal be quantum as long as possible before you turn it to classical and send it down wires, and or you put some simple quantum computation even behind the signal processing. So do you understand the distinction of there's a sensor, keeping the signal quantum, you can do quantum signal processing, followed possibly by the quantum computation.
So it sounds like your platform is almost set up for a pairing between an Oracle based sensor and a Hilbert based computing platform together.
That's correct. And as I say, we can start from the edge and work out, towards the data center, not necessarily targeting, say, big data center like you think of the IBM Q.
That's interesting. So, in a sense, I mean, you just said, sort of sensing, signal processing, and then potentially some computation. So, presumably, in that sort of an application, you could actually, I mean, what your use case is very specifically. So, you can make maybe not even a universal quantum computer, but a more narrowly scoped quantum computation for that particular purpose.
And there you have pinned part of our business plan and the difference, where you don't. Once you move away from having to be general purpose, apply any algorithm, you have a lot more tolerance over certain classes of errors and so on. And again, machine learning comes in there now to match what you have in your computation to the problem at hand. And targeted purpose is the way to get some power early on out of the quantum computation.
It's so cool. So, I mean, just for the benefit of us and our audience, I mean, just to help us speculate about what kind of new sensing technologies, what kind of new capacities will emerge, into the market based on these platforms. I mean, inertial sensing sounds very powerful for guidance control, but there must be much, much more, right?
Well, it's essential to have navigation in a GPS denied environment. So, starting with clocks, and believe it or not, also combining the clocks with quantum radio frequency sensing. And then finally, the inertial sensing makes the PNT solution, position, navigation, and timekeeping solution. The first things on the radar screen will make total sense. For example, you can send up in space special gravity gradiometers, for example, to measure climate change. Early versions, classical versions, were used to measure the mass change due to the melting of the polar ice caps, things like that. Environmental changes due to wildfires. The first things are terribly practical, but actually very sophisticated, and you keep on adding them because you would like to begin to recognize what are you not interested, what are you interested in. That's where machine learning comes in. Compressing the data is very crucial, where machine learning comes in. So you have all this quantum data, which can be enormous, absolutely enormous. How do you deal with it to make it digestible, if you like, on the compute end, whether it's quantum or classical compute end? So as I say, the first applications will be quite understandable and rational and just come from the bottom out of what are some of the important problems to solve navigation GPS denied environment.
You were mentioning climate change and monitoring the climate. It does make a lot of sense now. Frankly, just personally, I get the idea of the cold atom lab on the space station now with better context, because what better place to observe the Earth than up in space? And it's such a compelling use case, because if we can't quantify the changes that are going on in the climate, it's going to be very difficult to get a handle on how to slow changes that are dangerous or reverse things that are really dangerous. So that's really fascinating. Is that what phase is that development in? Is that still in sort of experimental? Is there any actual applications you're working on?
Oh, actually, NASA is supporting a fairly large effort to develop. NASA missions are very long term, so we look at 10 years down the line. So the answer is yes. And I also wanted to add, in the future, wouldn't it be nice to see the impact of various events on climate change much sooner by having much greater sensitivity? For example, what is the impact of a forest fire, or a hurricane over there? How does it impact other places? That's just to say that the sensitivity improvement you can get with quantum can be applied in so many places. Space, we're talking about climate change, but also in medical applications for doing, uh, you know, brain scans, for example. And you might see atoms replace the squids in MRI machines. Quantum has been used for a long time in those. That's a little bit, aspirational, but we shouldn't be shocked at those things. But that's the real key, is that where we'll see quantum. I often say in talks to popular audiences, quantum is going to be in the kitchen, sitting next to the toaster. It's going to be there in 25 or 30 years. It really will. That's where all the technology, lasers, are in your kitchen, et cetera. Quantum will be there as well.
And I'm not sure if you recall this bit of history, but I mean, at the onset of the PC era, back in the 80s, I mean, so many people were skeptical about the claim that there would be a computer in every home, and they just widely scoffed at it. But you're making a similar bold claim of many of the visionaries back from the early onset, right, of compute technology, that there will be home use applications for quantum computing.
There will be, and it will be boring. Instead of saying, ooh, quantum, you're going to say, oh, well, you only have a 2,000 bit computer there. That's
So, but Dana, help us ground that. I love that daring claim, but help us ground it. What would be the home application in 2 decades for friends and family for a home QC?
Well, as I said, it'll in the end be probably a little bit, except when it first comes out, it'll be shiny and exciting. But you may remember when your CD player finally made it into the house. You probably don't remember when the transistor radio made it in the house. There are a lot of problems that can be solved with, for example, with quantum commutation or timekeeping, precise timekeeping, for example, secure comm. So it just might be in the back of your the whatever we call it, then Wi-Fi modem. It'll be boring, but it'll be very important.
Best kitchen scale ever.
Yeah.
one grain of flour at a time.
That's right. So when it gets there, it's not going to seem flashy. It'll seem everyday, just like computers are today.
It's so interesting. You mentioned MRI. Ike Chung and others used NMR as the first sort of algorithmic computation on qubits back in the 90s, until they sort of maxed out the number of qubits they could actually manage on an NMR rig and said, okay, that's 7 qubits is as much as we're ever going to do. It would be really interesting to go full circle and end up with much, much more sensitive sensing technology in an MRI machine. And I mean, I can't imagine if you're at a quantum scale, potentially you could be imaging individual cells. You could spot, a first cancer cell if you had machine learning sifting through the data.
The field of machine learning, as you know, AI, and just going gangbusters. The interesting aspects is indeed marrying quantum with machine learning, not just for usual machine learning applications, but even to discover things about quantum systems, because quantum systems become incredibly complicated very soon. And fortunately, the technology for doing machine learning has become everyday and accessible. But I think you'll see an explosion in ways you might not quite have expected of the marriage between quantum and machine learning, beyond the computation, the quantum computing advertisement and so on of it. It's really moving unbelievably fast, those two together.
I mean, in many ways, I agree. We're living through miraculous times, right? I mean, the onset of the machine learning algorithm is so powerful. Quantum information science is just blossoming in so many ways. But also, it feels like we're living through an era of rapid advances in essentially quantum level engineering, right? The capacity to build these systems in brand new ways. Do I have that right?
You do, and I think part of what you're seeing is the following: putting AI for the moment aside. The UK in 2013, instituted in 2014, was the first government to recognize the economic and national security impact of quantum technology. And Europe followed, US followed, China was already well invested, Australia followed, India's followed. There is a race to establish leadership. And especially here in the US, having given up leadership in various kinds of manufacturing technology, there's a recognition that quantum is, in some sense, the final frontier. The way I articulate it is quantum physics tells you how well you can perform any task given a set of resources. And modern technology today allows us to get to the quantum limit, how well you can do any task, in a broader and broader array of applications. And in the near future, if you're not operating at the quantum limit, you won't be competitive. So it's not just that, as in let's say, the dot-com boom or the telecom boom. It's not a matter of just technology or just the financial world. It's really a matter of survival, of being at the forefront and not being behind. And so there's geopolitical aspects to quantum technology and AI, of course, as well as pure technology. And there's an anxiousness to accelerate the technology drive, which is why there's a substantial quantum market, we'll call it, where governments, including the US government, are putting in billions to secure leadership.
So these are almost nation state level concerns. This is not just economic competitiveness.
Oh, absolutely. Operating in GPS denied environment, being timekeeping has civil but also defense applications, as most of these technologies do. Absolutely.
It's true. I mean, when you think of it in those terms, as you said, it really is the final frontier, because once you get to the quantum limits of nature, I mean, how are you going to improve your performance beyond that, right? It's really just going to be how well do you use those phenomena that borrow from the way the universe operates. So that's your competition.
That's exactly right. So it'll be a matter of driving down costs, price, performance, being able to scale.
I noticed also I looked at Google Scholar. You have a listing there for psi as a service, which I thought was amazing.
Yes, quantum as a service. Exactly right.
Yeah, quantum mechanics as a service.
Quantum mechanics as a service. Yeah, and Oracle somewhat does that.
Yes, right. No, so we've been really fascinated by this thread. Thank you so much on this quantum sensing. All these applications really opened our eyes. But we're also curious to hear more about what kind of quantum computation and qubit level architectures and approaches that your venture supports. I mean, there's a lot of algorithms in play out there. There's a lot of ways that could go to help us understand in more detail how the Infleqtion platform and quantum computation could emerge as a set of practical outcomes for the market.
Okay. First, let me add something onto the previous conversation, which, from a venture point of view, is that not only does Infleqtion push on the computational technology itself, it very much works to enable others to push on theirs. We provide tools and components to competitors. Super.tech, you saw we acquired. Their software applies across the board. So keeping in mind that Infleqtion as a whole is very, very broad in its approach to enabling the evolution of quantum technology. So there's the core stuff that we do on the inside, but there's also the much broader enabling across the spectrum, as I say, from software to components. And for example, we have a program about to commence in Japan called Moonshot to help them build their quantum computer. So when you ask about our strategy, it's enabling very broadly, other people's quantum computing. Then you can say, what about our internal quantum computing effort? So the objective here is to target that, let's call it the sweet spot, that moves towards the edge of solving targeted problems with a modest number of qubits and modest fidelity. Modest meaning not that far away in some sense from what the, let's say, Quantinuum and IonQ have, but in a smaller qubit form factor addressing very specific problems.
It's so helpful. Thank you. And could you be more concrete? I mean, what kind of problems are economically, desirable with a, medium count of the number of qubits you can run?
So you have such a good question about economics. And frankly, in terms, the fact is, in compute, you can't realistically talk about good economics. You can on the sensing side and working your way out to processing. So we are still in a mode where we demonstrate milestones and achievements that are not actually economically viable yet. But here is the key about Infleqtion's approach. When we make a better quantum computer, we also make a better clock. And we make a better clock, we also make a better quantum computer, because the work is all directed at, again, shining pointing and shooting laser beams onto atoms precisely. And so the economics is going to be led, for example, by the clock technology first. When you say something economically feasible, where the company can make a product, put it to market, make a product, have reasonable margin, that's with clock technology. And it may seem so distinct from the computation, but I will mention, by the way, that the first entanglement of gates came out of the clock group at NIST, not the computing group at NIST. So I didn't mean to divert your question, but rather describe the company's tact on getting quantum into the market, getting finally to be cost effective on the compute side. And it will come, as I say, with things like clocks first, RF detection second, and other sensing technologies. And then the quantum signal processing, we'll call that analog. And very closely connected to that will be the quantum computing, the targeted, purposed quantum computer. So that's the economics at it. It's led by timekeeping, say.
I see. But their advances reinforce each other, right? Yeah.
So when we make a better vacuum for the clock, it happens with the computer and vice versa. And so again, to your electronics analogy, the equivalent of transistors, circuit boards, and so on, you can use them in different ways to get different functionality. The computer, for sure, is the hardest, but it still uses the same parts. Engineering still has the same classes of challenges as even the clock.
That strategy strikes me as so smart, because if you can tap into market demand for a clock or an interferometer or, as you said, it's TNC, I think is right. That's the acronym for TNP position. Then that starts a flywheel where you can fund the engineering work that you need to make the devices smaller, more reliable, cheaper to manufacture, and the quality goes up over time, and you're getting closer and closer to that threshold where computation becomes economically viable.
And so that's exactly right. And we have been, manufacturing those parts. And if you looked at our computer versus looked at our clock, you'd recognize the relationship between the two, even though the clock is much simpler. The technologies underlying it, there's enormous amounts in common. And that's going to be that way for years to come.
But it's also interesting just from the standpoint, I mean, we're both Silicon Valley people, are the two co-hosts of this program. And so we watch all these startups, some of which have very abstract value propositions that don't seem to make any sense and have a long time before they make money. Here, though, I mean, this subsegment, right, of the quantum computing, ecosystem, your segment of it feels like it's got immediate, direct commercial application. It's not like we're waiting for 1,000 more qubits of error-free computation to come online. Then we can do Shor's algorithm sometime in the next decade. It's like right now, it appears there's strong applications.
That's exactly right. We still need the market and the technology to drive down the cost of the lasers so they can be deployed everywhere. But it's not a question. In fact, that's why there's a whole sector of the community out there, particularly the defense community, that's in a big hurry, because it's not a question. It's a question of technology and not of getting good qubits to work. And by the way, in co-quanta, before Infleqtion was profitable, sold things, was profitable, for about 10 years until we took on money to explode. So we had customers.
That's got to be unique in the quantum space, completely. You made money?
Yeah.
Wait a minute.
Yes. And we have to get back there, but the path to doing it, there's no question that what the path needs to be. Get those integrate the lasers, bring the costs down, integrate the whole systems, because this country actually needs it. And even before integration down, fortunately, there's a clock market. There's a navigation, it's PNT, position navigation timekeeping market already out there where we know exactly how well we have to do to interest the people who, are in the market for these things.
That's so interesting. And am I right in assuming, I mean, Super.tech was founded by Fred Chong from University of Chicago. It's a really strong software team. My exposure to what they're doing was it looked like they were focusing on software architectures required for doing distributed computation or orchestrated across multiple devices. Is that sort of how they fit into the work that Cold Quanta had already done, is sort of, as you were saying, sort of constructing that sensing, processing, and then computation pipeline?
Well, they work on several layers of software, but those guys are simply outstanding. They are now undertaking the machine learning and machine learning simulators. When Oracle goes on the cloud, there'll be associated simulator with it. They have a lot to do with that software. And then there's marrying hardcore Schrodinger equation quantum with and abstracting it. So, it's already been abstracted for quantum computation, but in lots of arenas, it has not been abstracted. That's what they're extraordinarily good at. They're just an awesome team. By the way, it's Fred Chong and Pranav Gokul, who is the CEO. And just a really, really good team. I hadn't appreciated, being a hardware and tech guy, how much power there was, not just sort of fundamentally enabling, but also enabling economically a company to move faster than its old pair of skis.
Don't give the software guys too much credit. It'll go to their head, though.
They're great.
It doesn't work unless there's hardware to run it on. So keep that in mind. That's great to hear. So, I mean, I feel like we've gotten a really complete picture of the Infleqtion story, but also just the story of this cold atom technology, this from the initial sort of discovery through the increasingly sophisticated sort of productization of the technology. Is there anything sort of that you see on the horizon in the next 12 to 24 months in terms of shrinking of components or anything else that would sort of be a big leap forward for neutral atoms?
Well, first, I think you'll see not only the clocks come to a early maturation, still kind of big and market, also something we call quantum radio frequency detection, which is a totally different way of receiving RF signals. And so you should put out your antennas to see this technology actually rise quite quickly. In fact, as we speak, there are demos being made to agencies like DARPA, the Army, other DoD agencies, because they are often the first adopters. So you'll see those technologies come to the surface. And then in terms of miniaturization, the Department of Defense is investing very heavily in the CHIPS Act. And through the CHIPS Act has a quantum portion. And while it's a bit early to say what the outcome, I will be extremely surprised if there isn't a very good portion of those funds and that energy going into what's called photonic integrated circuit development at a very major scale. So look out for that. That's coming. And if you look at the recent work coming out of UC Santa Barbara in particular, for example, Dan Blumenthal's group, and at NIST, you'll see the tremendous progress they are at making miniature versions of the kinds of things we need to see commercialized and to become everyday.
So exciting. I can't wait to have a quantum device on my countertop. I'll be the first to buy it, I'm sure. Well, thank you so much for your time, Dana. We really, really appreciate it. We had a tremendous conversation and really, really learned a lot. So thank you.
Thank you so much.
It's been a pleasure, and all the best to you both.
Wow, that was so cool. That it's just mind blowing stuff. I mean, it's just it was wonderful to hear his prediction that in 1 or 2 more decades, quantum technologies are going to be common within the home. I was just amazed by that. A daring prediction.
Very, yeah, absolutely. I mean, I was struck by that, and I mean, I do see the reason for his optimism because very, very broad applicability based on, as he was saying, the sort of maturation, the engineering techniques that we have to operate near the quantum limit. And as he said, my takeaway line was, if you're not operating at the quantum limit, you're not competitive.
There it is. Yeah.
I mean, if you want to know what quantum 2.0, what the quantum revolution is, the new quantum era, that's it right there.
And what was really one of the most powerful moments for me was to realize that he's pointing directly at it, is that in a certain sense, these technologies are so strategic that they're really at the level of nation state level concerns, like numerous very powerful entities all competing for supremacy in this area of innovation. Just amazing.
Well, and also that the applications for sensing and signal processing include, in the near term, starting to get a better sense of how our planet is changing as the climate shifts. That's just so exciting to me because, you can't fix a problem you can't measure, and it's really hard to measure the planet at the moment. So any advances in that front are very welcome. So,
more power to it.
Stuff. So terrific. Thank you for joining us, everybody. We'll be digging deeper into the neutral atom modality and other modalities of qubits and other algorithmic topics in the future. So thanks for joining us. If you like what we're doing, please subscribe and leave a review on Apple Podcasts or whatever platform you use for consuming your content.
Good stuff. Talk to you next time.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.